Rosie,
Oliver,
Eddie.
and G.
and today we'll be talking about
The Schrödinger equation and the infinite potential well.
this is the time-independent Schrödinger equation. Understanding this equation is essential for many parts of physics. In this equation, V of x represents the potential energy of the system, E of x represents the energy of a particle, and psi of x is used to describe the wave function of a particle.
the wave function is a quantum mechanical representation of the particle's position. The time-independent Schrödinger equation governs the energy states of a particle. Using it enables us to predict the allowed energies and locations of the particle.
As you can see, the time-independent Schrödinger equation is a second-order differential equation. To solve it, first we rewrite it in this form, then we choose a suitable trial solution, substitute it in, and eventually we get the general solution. Pause the video now if you want to work through the maths yourself.
Now that we've got our general solution, we can apply the Born rule to it. According to the Born rule, the magnitude of the wave function squared should give you the probability density function. The integral of the probability density function over a region will thus give the probability of finding the particle in that region.
To achieve this, the general solution must be normalised like so. The new normalised wave function can now be used to find the probability of the particle in any given region.
The wave function also needs to follow some mathematical constraints. The function must be single-valued for each position x, must be continuous and have no breaks in the line, and must be a continuous first derivative with respect to x.
This is to ensure that the probability of finding the particle at any point in space can be unambiguously defined, and that other physical quantities may be calculated from the wave function. This also prevents infinities from occurring in the second-order differential, which implies that the energy approaches infinity.
Now that we know all the rules constraining the wave function, let's apply it to a free particle.
A free particle is one which exists with some energy E larger than zero, in a region where potential energy is zero. Substituting this into the general solution, we get this.
Plotting the modulus square of this wave function against position results in this shape. You will notice that the function cannot be normalised as its integral over all of x gives infinity. However, the graph is still able to tell us locations in which it's impossible to find the particle, since the relative probability density in these regions gives 0.
The resultant function cannot be normalised. This is because free particles are highly unrealistic. To get a more realistic function that can be normalised, we must consider the potential energy of the particle. The simplest way is to place the particle in a potential well.
To understand what a potential well is, we will look first at a classical potential well.
Let's consider the case for a gravitational potential well. Here, we have two hills separated by a valley. The gravitational potential at the top of the two hills is higher than that in the valley. The difference in the potential is known as the potential gap.
If we place a ball at the bottom of the valley and give it a light kick, the ball will roll up and then back down the hill. If we kick the ball hard enough such that its kinetic energy is larger than the potential gap, the ball will overcome the gap and leave the gravitational potential well created by the hills.
Just like the classical potential well, the quantum potential well also have regions of high and low potential. For simplicity's sake, let's give the high potential region infinite potential and the low potential region zero potential. Mathematically, these regions are defined as x smaller than 0, x between 0 and L, and x larger than 0. We shall call them regions 1, 2, and 3 respectively.
Classically, this would be like a valley in between two infinitely high hills. Because the hills are infinitely tall, the ball cannot go over the hill and appear outside the valley. Similarly, because the potential is infinite, no particle can exist in region 1 or 3. Let's now apply the general solution to the Schrödinger equation we got previously to this infinite potential well. Because the particle cannot exist in regions 1 and 3, the wave function there is 0. The wave function psi of x being 0 in these regions gives us our boundary conditions.
The potential is 0 in region 2. This means that any particle there is effectively free, and so it would have the wave function of a free particle. Remember that the wave function and its first order differential must be continuous. Therefore, at x equals to 0 and x equals to L, both the wave function and its first order differential must be 0.
Applying these boundary conditions results in the solution looking like this. The full mathematical method of applying boundary conditions is shown here. Feel free to pause if you'd like to work through it yourself.
The important parts of this solution is that it is of a sinusoidal form, and this n here. N can only be positive and it determines the order of the wave function. When n equals to 0, because our function is of a sine form, the waveform does not exist. Therefore, n is any whole integer larger than 0.
As you can see, because n is an integer, we are left with discrete energy levels, and this means the energy for a free particle in an infinite square well is quantized.
We can also apply the Born rule to it to achieve a probability density function of the form as shown. Due to the boundary conditions, we are now able to normalize this and find the probability of finding a particle in a given region. When sketching the probability density function against space, it can be shown that yet again, at each allowed energy levels, there are points in which the particle will never be found.
Today we have learned how to solve the time-independent Schrödinger equation,
how to apply the Born rule and the mathematical constraints onto the solution of the equation,
How to use the solution to determine the probability of finding a particle in a given region.
And how to apply all of that into an infinite potential well.
Thank you for watching.